All right, folks. Hopefully you can hear me. This is my first stream ever on Twitch. I did a test stream earlier just to do some end-to-end testing, but this is my first real one. I work at Amazon Amazon Web Services at AWS, but I just went to Twitch and set up a channel like absolutely anybody else would. No special treatment. So we'll see how things go. If you don't know me already, my name's Colm. I'm a distinguished engineer here at Amazon Web Services. Welcome to my office. This is in the AWS reInvent building in downtown Seattle. We do have COVID protocols, but I'm in an office on my own, so I don't need to wear a mask or do anything. I'm also vaccinated. We get these little stickers to prove it. I mean, the office is lightly attended, but there's people around. It's still kind of cool. Anyway, I'm going to talk mostly off the cuff, but I do have visual aids. I really dearly miss whiteboarding, so what I've been doing during the pandemic is as my best kind of replacement, I bought a series of sketchbooks where you can rip out the paper, and I've got colored markers and I make diagrams, and I'm hoping in the future to get a document camera, but I don't have one of those today, so I'm just going to hold things up. I'm going to talk about an aspect of AWS called SIGv4, and which is how we authenticate every web request that comes to Amazon Web Services. And I wrote a blog post. I put it out yesterday, but I wanted to go into a bit more detail and give a bit of a deeper dive to help people follow through. People who are here live have questions. Just feel free to put them in the chat, and I'll try to answer them as we go. But if you're watching this video later on demand, feel free to send me questions on Twitter or any other way you can get them to me, and I'll try to answer there too. All right. So where do we start? So, like the name suggests, AWS, Amazon Web Services, that's our main show, right? We build and run web services. And those web services are APIs that are served over HTTPS, right? They're mostly REST APIs, and people send requests to do things, and we go off and do those things, maybe like launch an EC2 instance, create an S3 bucket, put something in an SQS queue, read a CloudWatch metric, whatever it is, and then return some kind of response, 200 okay, that went fine or whatever. Every single one of those requests is authenticated using the AWS IAM system, the Identity and Access Management System, using a version of our signature protocols, the SIGv4 protocol, or now the SIGv4A protocol that we just announced. And it's just like an unfathomably large amount of things. I can't go into the exact numbers, but like we recently disclosed that we make hundreds and hundreds of millions of those requests are authenticated every second. So like just in the time it takes me to say one sentence, it's easily billions, and it gets uncountable very, very fast. Just a staggering number of requests that are being authenticated, and every single one of those, right, we got to check that the request is coming from the appropriate customer, right? So when AWS customer signs up for AWS, they go and create accounts, right? And those, and within an account, they can also do things like create users and roles and so on. And every single one of those accounts, users, roles, we call them principals, has an access ID, an access key ID, and a secret key, right? And that material is ultimately what a user uses to prove, to us, you've got, you're the right person. Now, they don't use those keys typically to like log into the system, like if they're logging into the console and whatnot. Hopefully they're using multi-factor authentication, and they can use some kind of some of the MFAs that we support, or they're just, they can log in with a password, and if they do that, hopefully they're using a very good password that's stored in a password manager, and so on. But I'm not going to cover that part. I'm going to cover the part that, well, after you log in, after you create one of those accounts or users, you can create these keys that are then used to access the system. If you're running code on EC2, we also have a system on EC2 where EC2 can actually provide those keys that are very short-lived and rotate frequently directly to your code that's running on an EC2 instance. But those keys go into either code using, say, an AWS SDK or something like the AWS CLI, the command line utility, and are used to make requests on your behalf, right? And so we're gonna start with, like, well, how does that work, and why does it work that way? So, like, the fundamental problem that we're solving, right, is authentication. We've got two parties. Hopefully you can see that. And both parties kind of want to be sure they're talking to the right person, right? Our customers or users want to make sure that they're really talking to the right, Amazon Web Services, that our APIs aren't being impersonated in some way. And that's done in a very routine, boring way using the magic of SSL TLS. When a client connects to one of our APIs, it's over HTTPS, and it can verify the certificate that we have the same way your browser verifies the certificate for any website. And there's nothing terribly interesting about that I'm going to cover today. Maybe in the future I'll talk separately about the intricacies of TLS and SSL and how that stuff works under the hood. But that's how the callers and customers make sure that they're talking to the real AWS. And then how do we make sure that it's the real customer at the other end? Well, there's a bunch of options for how to do that, right? And the common ones, right? The common techniques that are out there are, we could just have the customer or the caller send AWS their actual secret key every single time on every single request, right? Kind of like a password is sent on a login. That's a technique called bearer tokens, right? It's a common technique. It's got its challenges, though. The biggest problem with bearer tokens is, well, if there's some issue in the system where either on the client side or on the server side or in the middle that lets the bearer token gets disclosed, well, the game is up. Now that bearer token is out there and can be reused by anybody, and that's not great. We kind of have to tolerate that for passwords, right? Because you literally in some cases type a password in and then it just gets sent, and hopefully it's authenticated by a system that's using a password hashing function. It doesn't actually have to keep the password on its side, but it's still all of those components. They have to transmit and send or receive the password, and it's kind of flying around in plain text, and it's not very comfortable for me, at least, to think about that, because there's all sorts of bugs and issues that can arise in software or how people handle things that mean credentials end up in places they shouldn't, and it's doesn't fill me with the warm fuzzies. The next common technique that you see out there is to use like some kind of hashing, which is what we do. So I'll come back to that. We'll spend a lot of time on that, which is a way. Hashes are a one-way function, so they're just, you might have heard of some hashing functions like MD5. Please don't use it in general. That's kind of an outdated one, or SHA, and if in the SHA family, hopefully things like SHA-256, and they just take some kind of input and optionally a key if you've got a key-based hash function, and translate that into some other unique output, right? That isn't predictable and doesn't really reveal anything about the input, except that you know the input, right? That's kind of the important property of a hashing function here, and that's what we use. So I'll come back to that, and we'll see how we use that and how that works. And the other option is public-private cryptography, asymmetric cryptography. So that's algorithms like RSA, the oldest one, and the standard one that's been around a long time, or newer ones like ECDSA, which use elliptic curve cryptography. And that's just a form of cryptography where people create public-private key pairs, and if you've got the public key, you can verify that somebody has the private key, which is a neat property. Actually, it's public-private key cryptography clients are using to verify, when they connect to AWS, right? When TLS SSL is happening, the magic that's part of an SSL certificate, that's all public-private cryptography. So that's pretty cool. So those are the options. And now that we have SIGv4A, which I'll talk about too, we're also doing public-private key cryptography. I'll talk a bit about why that's so hard and what's involved. So that's the problem that we're solving, and so something I want to kind of ask your trust on as you watch this talk is, all right, I'm gonna go into why we designed our request authentication scheme the way we did, and a big part of that is security design, which involves threat modeling, right? And a standard part of threat modeling is to think about your worst day. Like, what's the worst thing that could happen? And how do we make sure, that the system fails safe or does the best possible thing, degrades gracefully or whatever on that day or in that situation? And that involves, talking through what ifs, right? Like, what if such and such a system was compromised, or what if such and such a system had a vulnerability in it? And that can sound like you're kind of acknowledging or just throwing away the idea that this stuff could or should be vulnerable in some ways. But that's not really it. Every case where I say something like that, you got to realize we put an unbelievable amount of effort into making sure that we don't have security issues or vulnerabilities in any part of our stack or in any single place. But at the same time, just like the folks who design ships, figure out where to put the bulkheads in case there's ever, a breach of the ship's hull, you still have to think about it, right? You still think about, well, what if this crazy thing that should never happen happens, right? How's the system going to fail safe? So there's going to be a bunch of that, and so hopefully don't come at me out of context on that stuff as you hear it. So an important part of the design criteria for the SIGv4 protocol, right? Remember, our mission here is we're authenticating every request, right? So the most important thing is we want to make sure we're correctly authenticating the user, right? We want to make sure that they really are who they say they are, they have the secret key, and there's no way to impersonate them, right? So that's the most important part, and that's what a lot of the cryptography and stuff I'm going to get into gets at. But we want other things too. We also realize that, people, ordinary mortals like us are the folks who write software that calls AWS services. And, issues can arise where, the request gets logged inadvertently somewhere, or something wasn't quite as well protected as it should have been. And so we also want to make sure that, our authentication scheme is relatively robust against, it being logged somewhere or somehow, sneaking out of a system. We want to make sure that, the fact that the request itself is known to somebody isn't that big a deal. That there's no, secret in it or visible in it, and that it's not easily replayable. You can't just go take it and then do something evil, right? You can't just steal a credential and go do something evil. There's a long history of issues like that in many, many security systems. We just didn't want to have that as something our customers would have to deal with, because it's not fun. And then other interesting properties, we think about are, you want to make sure you've got long-term security here, that no one can break these things even over long periods of time, and so on. And then you've got performance considerations. You want to make sure it doesn't eat a ton of CPU on a customer's box, or eat a huge amount of latency on a network connection or something like that, because that would be no fun. And so all that went into design. And then something else that's probably not obvious unless you either work at AWS or interact with us a lot is we think about isolation a lot. It's our go-to technique for both availability and for security. We think really, really deeply about how we compartmentalize our systems. We essentially kind of say to ourselves, anything you connect too strongly to anything else, they'll end up breaking at the same time. you know, and we mean that both in an availability sense. If the coupling is too strong, you know, you might take them both out at the same instance, and in a security sense, you know, if there's some kind of security issue in A, it could spread to B or have implications for B and so on. And one of the strongest examples of that is the isolation we put between AWS regions, right? So we've got a huge collection of AWS regions that are out there, right? This is just 3. But, you know, we're always thinking about these lines that are between the regions and how strong we can make them. And when it comes to this identity stuff and authentication, our job is made a little difficult by, you know, competing requirements from customers. So our customers tell us, you know, well, we want strong separation between regions, and we especially want to make sure we've got sometimes, you know, data sovereignty or jurisdictional separation, because they have like legal or compliance requirements that, you know, if they put data in a certain geography, like say in Europe, it has to maybe stay in Europe, right? And it can't ever leave Europe. And they have to be able to enforce and honor that, right? But at the same time, they might have systems in the US and they want to manage those with the same accounts, users, and roles, because having a lot of credentials to manage is its own security risk. So there's this kind of fine balance between, well, we could make users just have different, you know, passwords, keys, IDs, everything in every single region, like very strong vertical separation there. And we do that to an extent. We have these things called partitions. So for example, there's a partition for our commercial regions, right? And there's a partition for US government customers, you know, at all levels, like federal, city, state, right? There's our US GovCloud. We have a partition for China. And those accounts don't intermingle. You know, if you create an account in our China partition, it stays in China. It can't be used in our commercial regions elsewhere. If you can't create an account in our commercial regions, vice versa, it can't be used in China. So those have that strong vertical isolation, because customers have told us, well, that's where the balance lies there. But in general, within the commercial partitions, they want to be able to use the same accounts in, say, US West 1 and EU West 1, right? Because you want to be able to track things and see, well, this is the same identity here and the same identity there and so on, and have everything join up. But they still want very strong separation and very deep guarantees. And we don't, you know, when we make commitments like that to customers, that, you know, we really want to strongly isolate your data, and we want to make sure things can never leak across region boundaries. That's not just something we say. You know, although we do say it a lot, and it is, you know, something that's reinforced a lot in our culture and that people hear a lot here. But we want deep mechanisms that are definitely going to work. And one of those mechanisms that we have is to say, well, okay, well, the systems in region A, they're just not going to have any credentials or key material that would even let them like do something in region B, right? And we're just going to enforce that barrier and rule. And that's a big part of actually how the SIGv4 protocol is designed, as you'll see. And so the core of the SIGv4 protocol, and this is where reading the blog post might be a bit better so you can follow along, is the customer, you know, constructs a web request that does something per the web service API that, you know, some team in AWS has designed. So let's say you're launching an EC2 instance, you know, you write your run instance call with all the parameters that you want. And it's an ordinary web request. You know, it's just a URL and some headers, and there's a specification for it in the documentation and so on. And then, so you concoct that, right? Or the client concocts that for you under the hood in the SDK. And the first thing you do is you canonicalize that URL. You know, different libraries have different ways of ordering things, and if they weren't in a consistent canonical order, we just really wouldn't be able to sign anything consistently. So the first step of SIGv4 protocol is just canonically order all those things. You know, we have a set of rules, it's published and it's in our SDKs, and people can figure out how to do those things. And then, so that constructs a URL, a canonicalized URL to sign, right? And then the next step is you use the SIGv4 protocol to produce this signed header that goes along with the request and asserts, you know, everything. Here's a signature that covers everything in that URL and some headers that matter, that you could verify to make sure no one's changed it in between and we're doing exactly what the customer wants. I'll get into that into detail, but before I do, one thing to notice there is that we're signing the specific request, right? We're not, a lot of authentication schemes, what they do is they authorize a channel, right? So mutual auth or MTLS does that, right? You authenticate the whole channel, or a VPN does that. You know, a VPN authenticates the whole channel, and then anything that then happens over the channel has a kind of inherited authentication. And we didn't want to go down that path. You know, we didn't want to use like cookies or MTLS or that kind of a simple scheme, because they tend to be vulnerable to request smuggling and request replaying, where vulnerabilities in protocols mean, you know, nefarious requests can be inserted on the same channel and bad things happen, and that's no good, right? And then the other challenge with them is you're not really authenticating the request in that model. You're not authorizing the specific transaction. It's just a bad place to start. And you know, we have workloads and customers that are so sophisticated that they are like really individually signing particular actions, right? So a good example of this is like a bank transaction, right? Like you want to sign that specific transaction. Like you're moving, you know, $50 from my bank account into somebody else's bank account. I want to sign that specific thing because that's all I authorize. I don't want to have to authorize and say, you know, here you've got permission to transfer any amount of money you want, or you've got, you know, permission for 10 minutes to do whatever you feel like. You know, the more specific, the better, right? And that was our philosophy there, and that stood a test of time. You know, that's I've seen other protocols and schemes issues arise where, because they don't have that property, they end up in a little bit of trouble. So I really like that request model. Of course, one of the downsides is, you know, we have to authorize every single request, right? So that's how we end up with the billions and billions of things to go authenticate. And so let's get into how it works and why. I think I've given you enough context at this point. So the next thing that happens in the SIGv4 protocol is we actually construct the signature, right? So we've talked about how we canonicalize the URL. So at this point, you've got the URL and the request canonicalized, and you've got your secret key, right? But we have to take those and produce a signature. And so the algorithm's really straightforward. It's published. I linked to it and I put it in the blog post. And the first thing we do is we basically derive another key from your secret key that includes the date, right? So we take your secret and we couple it with this thing, with this AWS 4 string, right? So AWS 4 plus your secret and the date, and that all goes into this fancy HMAC algorithm, and we get this K date thing. So let me stop there and tell you what's going on. So first, HMAC, right? So HMAC is kind of an algorithm that surrounds a hash function. It's an unbelievably awesome piece of cryptography. One of the main designers behind it, Hugo Kravich, he won the Levchin Prize a few years ago in large part for his work on HMAC. And what it does is it takes a hash function, right, like MD5 or SHA or whatever, and kind of reorganizes it in a way with a key that in a very secure way can be relied upon. It even assumes that those hash functions are going to be broken over time, like MD5 was, and actually does things to compensate for that. Like it, you know, derives some stuff from the key and it puts that before the hash and after the hash as it's doing some mixing and some really cool stuff. But the end result is, you know, you've got this function that takes a key and an input and emits what's often called a signature. Pedantic cryptographers might also refer to it instead as an authenticated digest or an authenticated code or a MAC. But essentially, it's a strong way to have a keyed hash function. HMAC is used more and more these days. Actually, the HMAC-based key derivation function, HKDF, is like the main standard one now, and it's used in all sorts of protocols for deriving keys. So it's been a really great algorithm. So it's a great one to choose, you know, when SIGv4 was designed. And so by deriving like by the very first step there, right, where we're going to take your secret key and we're going to derive this other key that's bound to a few things. So it's bound to this AWS 4 string. So that means the final signature that we're going to create could not possibly have been for any other protocol. Like if we have another version of the SIGv5, SIGv6 later, you know, this key or intermediate key or signature is useless for that, right? It can never be used across versions, which is great. You want that. You want very strong version binding in your protocols. You know, protocols that haven't had that have generally suffered from downgrade attacks. And then the other thing is it binds to the date, right? So this intermediate secret, only good for a single day, right? And that's an important property because these secret keys, you have to know them, we have to know them. They're a shared secret, right? So when you create them, when you create a user or role in the IAM system, you get a copy of that key and a small window of time to kind of export it and get it into your tools. And we take our copy and we lock it away pretty deep inside the IAM system, encrypted, several layers of security around it, all sorts of security mechanisms around that system that render it inaccessible to us. All sorts of cool things I'd love to talk about and probably will at a future time. But fundamentally, that really inner deep part of the system has to know that key, right? But we don't want that. We don't want that. Like that's a radioactive thing. Like you don't ever want to have to deal with that key itself too much. So the way the IAM system works is, you know, every day generates these intermediate keys that are only valid for a day, right? And lets those get out a little further. Those get into another part of the IAM system that's for like distributing credentials, you know, sending and generating credentials that are then sent to the regions and so on, right? Which actually gets into the next thing. So the next thing is we now take that kdate string and we generate another intermediate key. This time we bind it to the region that's going to be used for, that the signature is going to be used for. And what that means is when the IAM system is now doing that daily key generation, it actually can then generate intermediate or sub keys that are valid only in a given region, and then can send those regional keys only to those given regions, right? So US West 1 only knows about the material kind of from there on down, right? There's a system, part of the IAM system somewhere in US West 1 that you know, only knows about this material, right? It doesn't know about any other region's material, and so on. And that's how you get really strong regional isolation. That's how you know, like, there's no part of the system in region B that could somehow, you know, use the material in region A, and so on. And from there on, we bind to the service. So we do all this again, and then we bind to the service name, right? And then we're pretty much at the end. The last step then is to bind that intermediate or subkey all the way down to including the URL, the canonicalized request we wanted to sign. And so what that means is the actual signature that's sent by the client, this all happens under the hood in the SDK and CLI. Customers don't have to think about it. Is bound to, you know, their secret key on a given date, in a given region, in a given service, right? And that's what's sent to, you know, and then is, you know, a HMAC signature over the URL, and that's what's actually ultimately sent to the service to authenticate. And so on the service side, when that request comes in, we have a library and a system that's secured off kind of from the average, you know, service team at AWS that is in charge of authenticating a request before the service team ever sees it. Right? When the request comes in, you know, one of the first things it sees is our piece of software that actually authenticates the request. And the SIGv4 authentication is kind of step one of that. It happens before authorization, before any kind of IAM policy or anything like that is even looked at. In fact, we won't even load IAM policy or do anything like that if this step fails, right? Because then we've no reason to believe it was even remotely a legitimate request. And so obviously that system to authenticate your request needs to have some of this intermediate material, right? But the only thing it actually needs to have is the most finely scoped credential, the one that's only valid for one day and one region for one service. That's all that little piece of software ever knows, right? And so kind of like earlier when I was talking about, well, you got to think about if the ship was breached and there was a problem in the hull, like where are the bulkheads? Imagine there was a problem in that software, some kind of security issue, right? The intermediate material that it knows about is extremely finely scoped, right? So we've got a very tight system of least privilege there, so that the consequence of that material, say being disclosed, is really no more serious than the potential issue in the system itself, right? If the system itself has an issue, in theory that system could maybe be abused to do something, right? But this is no worse, because again, the action would have to be scoped to say that particular service on that particular day and so on. But there's no like long-term bearer token or something like that could be stolen, or even like a password hash that could be stolen and then people try to brute force or crack it later. None of that's possible. It just literally just doesn't have any of that in memory, right? And so you can kind of see now the overall design of the SIGv4 protocol. You kind of have it there, right? We're trying to do things per request. We're trying to do things in a way where even if the URL and signature were disclosed or compromised, it wouldn't matter too much. In fact, that signature, all it can ever authenticate is that specific action, right? So like even if an attacker got it, okay, well they could replay it in theory. I should say SIGv4 requests aren't replayable after a very, very short time window. There's basically just enough allowance for people to have some clock drift. And not much more than that. But even if an attacker somehow got one and then replayed it, it would just do exactly what the person had authenticated it to do anyway, right? Which is this really, really nice property. And then you can see also how the design, this part of the design especially, it's really to make sure that we can stand over the isolation between systems, between services, between regions, between all of those things to be able to give people really, really strong guarantees using cool cryptography. So that's AWS SIGv4, right? So now the downside, one of the other downsides of this though, is these requests are bound to a region, right? I can't just say, okay, take this URL and try it in US East 1, and if it fails, try it in US East 2, right? It doesn't work like that. You have to come up with a new signature for US East 2 because that region is in there and it's bound to it, and there's nothing you can do about it. And that's intentional. That's part of the design. We don't want it to be so that, and our customers don't want it to be so that data could just like silently move from US East 1 to US East 2 even. We always want things like that to be extremely intentional. But just last week we launched a new feature for Amazon S3 called multi-region access points. And more and more at AWS, although we have this very strong culture and principle of isolation between regions, we've been also launching these sophisticated products that can give customers multi-region offerings in what we think are safe ways, right? And just for some insight, what that means on our side is, we try to make sure these systems are asynchronously coupled across regions where possible. There's an unbelievable amount of testing that goes into making sure that there can't be multi-region impact because of these services or to these services, or that they'll always withstand regional impact, since the point of them often is to provide resilience for that for some customers who need geographic resilience, or have latency requirements and so on. And S3 multi-region access points are an example of that, where customers can use S3 in a multi-region way. They can have the same request be sent to Dublin or be sent to Virginia, and it'll work, right? And it's got some built-in resilience and failover capability and so on to make that magic work. But on our side, that means the same signature has to work for both of those requests, right? So one easy way to solve that would be, okay, well, why don't we just forget it? We'll take the region out of the out of the signature, and we'll just have them sign it with like a global string or something, and it'll be a little bit of a different signature, but it'll work everywhere. But then we'd be breaking our rule, because we'd have to have the same intermediate key material in multiple regions, and you'd no longer be able to say, well, look, if there's an issue over here in region A, anything that was anything impacted should have no impact on region B. You just wouldn't be able to have that strong guarantee anymore, and we really, really didn't want to compromise on that. So instead, with SIGv4A, we're using that other option, right? Public-private key cryptography, which is not a common thing at a per request level, right? So the magic of public-private cryptography is, unlike bearer tokens and unlike hashes, there's no need for a shared secret, and there's no need to pass a plain text secret around. Instead, you can create public-private key pairs, right? And you can put the public key on the verifier, right? The verifier gets the public key, and it's public. It's fine. It's safe for that to be public. That's why it's in the name. And it can verify that somebody possesses the private key, that they can construct a signature with that private key, and the verifier can verify it. And so what we're doing with SIGv4A is we're distributing public keys for the customer, right? So when the customer opts in and uses S3 multi-region access points, we're actually generating these public-private key pairs. We actually derived them in a similar way to this, first using HMAC and HKDF and systems like that from the secret key ID. And their clients get the private key, and our services get the public key. And what that means, if there were some kind of issue in any of those services, all that would be there is a public key, which is perfectly safe to disclose, can't be used to impersonate or do anything, or cross the streams or move data from region A to region B or anything like that. And it's kind of simple, like at a cryptographic level. It's essentially swapping in, instead of using HMAC, using in our case an ECDSA elliptic curve signature on the request. Those are more expensive in general than like just doing a HMAC, but we're on the expensive end. It's verifying an ECDSA signature that costs CPU, and we've done a lot of work to optimize that. Including on Graviton 2. Actually, we've recently really optimized how fast that can go on Graviton 2, and to be able to handle the scale of requests that come in. For customers and clients, it's not noticeable. Even phones are now at the point where they can generate an ECDSA signature very cheaply. But that's been the main difference for us, right? Figuring out that that distributing the public keys, getting them out to the verifiers, and then using them to verify and do the CPU, and do the CPU optimization so that we can cope with that at scale. And that's the difference. That's why there's a change. You might, if you're using S3 multi-region access points, you'll see how that goes. I did see some questions on Twitter from folks about is this going to show up in other services and so on. Simple answer is yes. We want to get SIGv4A out to more things and support more things over time. But we've got we've got a period of carefully monitoring it first and seeing how our customers, clients, and callers deal with it. If there's anything we have to optimize for them there and so on. It should be fun. Ben here asks, is SIGv4A not yet documented? So it's my colleague Jonathan Henson, or Henso on Twitter, he actually posted yesterday the full links to the algorithms and reference implementations if anybody else would like to go do it. So that's out there. I don't think we have precise public documentation on all the derivation steps and the algorithm in our IAM documentation, but I think we will. But we are at the moment this is all gated and only works for S3 multi-region access points. But I think as we go broader, we definitely want to be able to do stuff like that. I had another person ask me on Twitter how if I could talk about a bit of the post-quantum security and all that kind of stuff. I think I'm going to talk about that separately because that's going to be such a deep topic that I'd love to get into, and all of the cool hybridized ways where we're able to deploy cryptography these days, where even if somebody invents a quantum computer in the future, they're not going to be able to go back in time and break everything open and so on. That's more or less everything I had on SIGv4 and SIGv4A. This went better than I expected in terms of Twitch experience. So I'm hoping to do more of these. I've got a few queued up. Some stuff that I've done internally like this that external folks might be interested in. So one is all about cryptographic side channels and how those work in a simplified way that doesn't require too much understanding of cryptography. I also talk about item potency and how distributed transactions work and what's hard about it, and some stuff like that. And there's more things I want to get into too. But right now I'm just going to answer questions for folks. Will SIGv4A work in a mode where AWS never has the secret? So when you generate SSH public-private key pairs, that's a good example of that, right? If you're using your own SSH client to connect to EC2, for example, it's routine that you might do like SSH keygen on your laptop, right? And your laptop knows the public-private key at that point, and you take the public key and you put that on your instance, and that's all your instance ever knows, and that's how you authenticate yourself over SSH to your EC2 instance. I would love to be able to do that for this, and to be able to have public key import, and then have it work in a mode where we simply don't know your key. That would be an awesome iteration. That's not the current iteration, for a bunch of pragmatic reasons, mostly so that it interoperates with the secret keys that customers have today. They don't have to add a whole new level of key management, which I think would have to be done separately. But it'd be a really cool feature. I should scan the previous questions. Those are more comments. Cool. All right. Well, Twitch tells me we had like 50-something people total, so that's more than show up for my internal versions of these. So that's kind of cool. And there was no notice, but I didn't realize we'd get a Jeff Bar bump. So. Cool. It looks like it doesn't archive these. I thought I had enabled that. I think it just only shows up in the video section or the VOD section after we're done. But I'm pretty sure I enabled it because my test video earlier was saved, and then I went and deleted it. So cross our fingers, because I'll double check before I close the stream. How's that? And we'll see if that makes a difference. Twitch is a really cool platform. I'm biased. I work at Amazon. Twitch is a really cool Twitch platform. Is part of Amazon now. I'm biased. So I work at Amazon. Should declare my bias. Twitch is part of Amazon. But I have used other live streaming platforms, and nothing was this simple. And the Twitch Studio Beta in particular, like, it's just awesome. It's way easier than things like the open broadcast tools, and just nice and simple. Yeah, it says storing past broadcasts, so I hope we're good. Will there be a similar talk at reInvent? I'm going to talk about this at reInvent for sure, and probably not in this kind of depth. I'm going to try to use these things to get into greater depth than I usually can with an audience. Even at a 400 level talk, it's hard to get into to get into this kind of depth. But I'm definitely going to talk about this topic at reInvent. And actually, something I didn't mention that I'll tease up is one of the other kind of least privilege mechanisms that we have built into IAM is we take very seriously a service team's ability to act on behalf of a customer, right? It's not like we would never just let a service team say have some kind of role or permission or principal that just lets them do anything they want to a customer's data or have kind of carte blanche access. There's all sorts of criteria and controls around that. And one of the coolest controls is one we call FAS, forward access sessions, where we actually have a cryptographic chain of custody that says the team can't even go touch the customer's data unless the customer has called them extremely recently with an instruction that like kind of transitively relates that back. And it's how things like, EC2 is allowed access your EBS volume, for example, and it's really, really cool. We have an increasing amount of like cool controls that are all around like protecting AWS from AWS, like all these kinds of internal controls. Nitro is another huge example of that, where the Nitro system we built for EC2, even I'm literally at the most senior level of engineering in EC2. There's no way I can access a customer's EC2 memory or data or anything like that on Nitro. Just absolutely no way. Like, it's got all these rigorous controls, and that's something I'm going to talk about too. Cool. All right. What do I think is a cool IAM feature that doesn't get enough use? There's a lot of services and a lot of things support context keys that can be used in IAM policies, and I think those are fairly underused. I don't see context keys nearly often enough in IAM policies. That's probably one of my favorites. Cool. All right. Thanks, everybody. My time is up. My next meeting is due. So thanks for watching. I'll take any feedback. This is first in a series of experiments. We'll see how the rest go. Bye, everybody.